All right, today we're going to start our discussion on projectile motion. We are still in the motion section, so you won't need to make a new tab or anything like that. But we're going to kind of shift our attention from things that are moving just horizontally, like little cars or people going around tracks or walking, to things that are leaving the ground. Okay, we're going to discuss the motion of things that are flying through the air. And this study is called projectile motion. Okay, so things that are going up and down as well as side to side. So objects in flight could be bullets and arrows, they could be footballs, baseballs, soccer balls, anything going through the air like that. Raindrops, people jumping on trampolines, everything that is in flight, that's in the air, that has left contact with the ground has one major thing in common, and that's gravity. But the question for a very long time with scientists remained, how does gravity affect every object? Does it affect it the same? Is gravity pulling the same amount on a baseball as it does on a soccer ball, or a gymnast as a raindrop? Do these objects fall at the same rate or at differing rates depending upon their mass, how big they are? For a long time, people believed that gravity did not treat all objects the same. In fact, they believed that that pull of gravity was related to how big the object was. Something that's very large would have a bigger pull of gravity and would fall faster. It would what they called strive harder, while things that are very small would not strive as hard, and they would not hit the ground at the same time. They would not fall at the same rate because they don't have as much gravity pulling on them. However, in the 1600s, a man named Galileo was able to prove that all objects fall at the same rate as long as you account for something called air resistance. So I've got a demonstration I'm going to show you guys. And what we're going to do is I have a book, okay, and I have a piece of paper. Let me grab one that's not somebody's homework. All right, piece of paper and a book. Will these objects hit the ground at the same time? Well, obviously, the answer in this case is no. If you watched, the book and the piece of paper did not hit the desk at the same time. But the difference is because this light piece of paper doesn't have a different effect of gravity. It has what we call air resistance. The air is resisting its motion, and it's light enough that that air can stop or slow down its motion. If I take air resistance out of the equation, if I hide the piece of paper, then they fall. Let me move this down where you can see the table. Then they fall together at the same rate. Okay, so the difference here is not their mass per se. The difference is how their mass is affected by the air that it's falling through. Here, this is heavy enough that the air can't hold it back, but the smaller one is light enough that the air can push it and slow it down. If you have a complete vacuum, if you have a chamber where you've pulled all the air out, there's no air resistance, or say on the surface of the moon, we were able to repeat Galileo's famous experiments on the Leaning Tower of Pisa. Maybe a tall tale may not have actually happened, but that's the story, kind of like Newton with the apple. But we can repeat those experiments and see that, yes, in fact, things do fall at the same rate if you neglect that air resistance. So I've put these two links up on your, wherever they appear, up here. Just pause this video, go watch those two videos, and then come back and take more notes. All right, so when we use our calculations, we find not only that all objects fall at the same rate, but we also find what that rate is. And this, if you remember from our formula finder, we wrote it in that bottom, and I said, don't worry about it now, we'll come back to it later. It's later, welcome. That rate is 9.8 meters per second squared, meaning that as something falls, each second it's going to go faster and faster and faster. Okay, that does, as we mentioned with air resistance, have a limit. That's called the terminal velocity, the velocity at which it can't go any faster because of the air resistance that's opposing it. But again, in the absence of a vacuum, things would just keep falling faster and faster and faster as they go down. So here's a problem we're going to try, and I will have you try this, and then we'll talk about the answer. If Galileo dropped a basketball from the Leaning Tower of Pisa, which is about 56 meters, how fast was it going when it hit the ground? Okay, so for that, we're going to need a couple of things. We have the distance that it fell, and we want the final velocity. But they do give us one other thing that we don't have listed in the problem, but we know, and that's the acceleration of gravity. So we've got A, which is 9.8 meters per second squared, and we've got D, distance, which is 56 meters. What we're looking for is our final velocity, okay? What we don't have in this problem is time, so we're going to use that formula at the very bottom left of your formula finder, which is the VF squared equals VI squared plus 2AD. Pause the video, try this, and we'll see if you were right. All right, did you get it? So using VF squared equals VI squared plus 2AD, our initial velocity before Galileo dropped it was 0. So we do 2 times A, acceleration, 9.8, times D, 56, and then that equals VF squared, so you need to take the square root of those multiplied numbers to find the actual final velocity. I got 33.13, so 33 meters per second. All right, so in that equation, in the VF squared equals VI squared 2AD, blah, 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 did we use mass anywhere? Why? Why not? Turns out mass does not affect our motion equations. All that matters is that acceleration due to gravity. It's important to remember, though, that gravity doesn't just speed up things that are falling. Gravity also slows down things as they rise, and it's the same rate. It's the same gravity, same earth, same pull, same thing. So as things go up, on the way up, like this little pop fly here that he's experiencing, as they go up, they're slowing down. They get to the top of their path, and just for like not even a moment that we can measure, they have no velocity. Okay, they've slowed down to a stop and changed direction and start falling back the other direction, speeding up at, again, 9.8 meters per second squared. So they slow down, and then speed up. Same acceleration because it's the same gravity. It's the same earth. So now try this one. We've got a tennis ball thrown straight up with an initial speed of 22.5 meters per second. So we've got an initial velocity. It's caught at the same height from which it's thrown, so we don't have to worry about height differences or anything. You're just going to go up and then back down to the same height. How high does the ball rise above the height that it was released? And then how long does the ball remain in the air? Okay, try this one real quick, and then I'll give you some hints. All right, for the first part where we're looking for the distance, we have our initial velocity. We know at the very top of the path it comes to a momentary stop, so our final velocity at the top is 0. And we know the acceleration because we know that it's an object in flight. So with our VF, our VI, our A, we're looking for distance. We can use that VF squared equals VI squared plus 2AD just like we did before. Okay. With that, we can find that it went up and stopped at 25.83 meters. Okay. Try the math yourself, make sure you get the same thing. With part 2, how long does it remain in the air? Now we're looking for time, okay? For this one, again, we have VIVF, we have acceleration, we're looking for time. So this one's a lot simpler formula. We've got VF equals VI plus AT. With VF equals VI plus AT, we put 22.5 in for our VI, we put our 9.8 in for our A. We need to subtract over the 22.5 and then divide by 9.8. And for the time that it takes to get from here to the top of the path where it stops, we've got 2.3 seconds. Now, that is the time it takes the ball to go from where it was initially hit to the top of its path where it stops. But how often have you seen things just kind of hanging in the air? You know, baseball games are over and there's balls just left in the air. they don't do that. They come back down. So if it takes 2.3 seconds to get to the top, how long was it in the air total? Well, what goes up must come down. So if it's 2.3 to the top, it's 2.3 to the bottom, and we have a total time of flight of 4.6 seconds. Okay, so remember that when we're finding the time that it takes to go from one point to the other, what goes up must come down. It's got to come back down on the other side. Okay, we're going to pause there today, and pick up horizontal projections on Monday, as well as projections that are up and down at the same time. That'll be a lot of fun. So hopefully this will at least get you started on projectile motion and things that are flying in the air.